Welcome to Discovery Canada. I'm Jay Ingram.
And I'm Jane Gilbert. Investigators may have tracked the origins of a killer wave. For several years, scientists have been investigating the most destructive Pacific tsunami of the past decade, the Papua New Guinea tsunami of 1998. Giant waves reached 14 meters in height and killed more than 2,500 people. Now, some believe the tsunami was the direct result of an earthquake. Others argued that an earthquake in the area wasn't powerful enough to have set off such giant waves. One group had a theory that an underwater landslide caused it. Now, armed with new evidence, they think they've proven their case, and they're hoping their research will prevent more death in the future.
Dr. Costas Synolakis is a professor of civil engineering at the University of Southern California. He joins us from London, England. Dr. Synolakis, could you take us back to that time in '98 when the tidal wave hit Papua New Guinea? You went there. What was it like?
Well, it was the worst devastation I had ever seen, and I had been in all the tsunami sites in the last 10 years. There was absolutely no evidence of life, of houses. I mean, it was hard to believe that people ever lived in that place. The silence was deafening. I mean, it was as if even the wildlife was gone. I mean, it was truly a catastrophe of biblical proportions.
Now, what new evidence do you have that suggests that it was a landslide, not an earthquake, that triggered that wave?
Well, when we were there, we knew that the destruction was way bigger than the one that we would have expected from simply just from an earthquake displacing the seafloor. So we were suspecting a landslide, but of course we needed more evidence to try to find out when the landslide happened and how big it was. When we looked at the bathymetry maps, there were marine geologists who produced images of the seafloor. We could see that there was a landslide there, but we really didn't know if it had taken place now or 50 years ago. So we started looking for seismic evidence. And then Emile, Okal, my colleague from Northwestern University, brought over some records from Wake Island. And in there was a record from a hydrophone. And we looked at it, and I mean, it was the strangest thing. I mean, it was freaking unusual. It was something like we had never seen before. And we knew that this was not the record from, let's say, an aftershock or an earthquake. So it was something different.
Was this a sound then that had been recorded?
Well, it's a sound that we cannot hear. We have to. It's a sound that probably, perhaps, some animals would have heard. Some of the eyewitnesses in Sisano described the sound as if it was some sort of gargling sound. I mean, I remember someone saying that and using the English word gargling. So I don't know exactly what it was, but certainly what the hydrophone picked up on Wake Island, that was not within the range of sounds that we can hear. It was much longer than an earthquake, and to compare it with a piece of music, it would have sounded more like you know, a long piece of classical music versus you know, some modern rock song or something that has a quick and fast beat, which is what an earthquake would sound like.
So once you had this sound, how did you actually manage to tie it to the landslide?
Well, you see, the sound was everything, because the sound gave us the start point and the end point. What we had been missing is we didn't know exactly when it started. So once we knew from the sound recording that this is when the landslide starts and this is where it stops, then we take that information and we put it in our computer models, and we create a three-dimensional model of the ocean surface. And then we take it to the coast, and then we find out what time the wave arrives at different locations. And then we compare that with what the survivors tell us. The survivors would tell us that the wave arrived here between the first and the second shock, or the wave arrived here after they had felt two shocks. So we have fairly good arrival information for the wave. So then, I mean, we could validate our theory. We could validate that indeed this was a landslide because it fit all the parts of the puzzle. We had the evidence on the seafloor. We had the acoustic signature that told us exactly when it started, and then we had the arrival information. Bingo, we had solved the puzzle. So we were very happy with that. And it was basically the fortuitous existence of the Wake Island record, because we had the starting time of the landslide. You see, what is very difficult with landslides is that a lot of times, in fact, most of the times, they are not triggered immediately after an earthquake. It could take a few minutes. It could take a few hours. Sediments get destabilized, and then at one point, they just fail. And then it's very difficult to reconstruct exactly what happened, because very rarely you have that initial time. And this is what we got from Wake Island.
Now, Dr. Synolakis, this was a devastating tidal wave, as it turns out, caused by a landslide. The fact that you've been able to tie these together, does that give you a way of being able to predict such tidal waves, such tsunamis better?
Well, it doesn't really give us a way to predict it in terms of finding one in the future, but it does give us hope, particularly for those of us who live in coastal areas close to continental shelves, like, for example, in the west coast of the Americas, of North America, or the east coast of North America. There have been landslides in Canada, for example, the Grand Bank slide in 1929. There have been landslides on the west coast of the United States, most recently, we believe, in 1832. And the hope is that if we have hydrophones out there, and now that we know what to look for, we are going to have one more piece of data to evaluate if there is an unusual event that is happening offshore, to be able to say whether a landslide is triggered or not. So, in a way, this gives us another tool to be able to issue better and more targeted warnings, so we can get people out of harm's way.
Thanks very much, Dr. Synolakis.
Jay, you're always welcome.
Bye-bye. Dr. Costas Synolakis is a professor of civil engineering at the University of Southern California. He joined us from London, England.
In Science News, looking up into our family tree, way up. As you trace human history back into the distant past, our ancestors look less and less like us. And if you trace it back far enough, you'll come to animals that don't even look vaguely human, the earliest mammals. A new fossil may be the oldest human ancestor ever discovered, a mouse-sized animal that lived 125 million years ago. That was the same time as dinosaurs roamed the earth. But our ancestor probably kept out of their way by climbing trees and living on a diet of insects. The skeleton shows the ancient mammal had long fingers for climbing trees. It also had a thick furry coat. The new mammal is known as Eomea scansauria, which means the climbing ancient mother. That's an appropriate name for a tiny tree-dwelling animal that gave rise to all placental mammals, including us. Some new pictures from the Hubble Space Telescope are showing us some of the oldest stars in the universe. The observations show white dwarf stars. They form when a star the size of our sun reaches the end of its lifespan. As the white dwarf gets older, it gradually cools, making it appear redder and dimmer as time passes. By taking a series of long exposures, the Hubble team was able to see the dimmest, most ancient stars in unprecedented detail. And their temperature shows the stars must have formed about 13 billion years ago, which means the universe itself can't be any younger than 13 billion years. And that matches earlier estimates of the age of the universe made by Hubble, based on studies of distant galaxies.
What we actually measured was the age of the cluster, but we know that clusters like this don't form instantaneously after the Big Bang. Theory and other observations tell us that they form about 1 billion years after the Big Bang. So we should add 1 billion years to our age to get an age which is just under 14 billion years. And that agrees virtually perfectly with the age gotten from